Hello, folks. Welcome to Rational Science, the only site on the internet that does physics. Everybody else moves concepts around. They think they're doing physics. We have a great day today. We're going to be doing a little bit of gyroscopes, something NASA ran a few years back, about 20 years now, and it's known as Gravity Probe B. And what they did is, according to them, this is their conclusion, they moved time around. They dragged time around the Earth. That's the conclusion. You spent $1 billion to reach that result, that conclusion. Okay. Anyways, we're going to start with our extinction segment. And I forgot, Merry Christmas and a Happy New Year to everybody. I hope everybody has had some happy holidays. I surely did, in the company of my family, so we did well. I hope you did it just as well. Anyways, we're going to do a little bit of extinction, talk about some of the subjects related to extinction, and then we're going to move on to some of the questions that people asked, some of the comments people made. I'm going to try to address those, and finally we're going to get to our gyroscopes and Gravity Probe B and the dragging of time. Okay, so let's begin with our first one here, and we have this gentleman. His name is Jeff Bezos. Discusses plans for 1 trillion people to live in huge cylindrical space stations. And Jeff Bezos says the following: we'll all be living inside massive cylindrical space stations one day. And he says these habitats could allow an astronomical number of humans to survive. So we're going to be out in space, trillions of people, forget about billions. And he said if we had 1 trillion humans, we could have at any time 1,000 Mozarts and 1,000 Einsteins. I don't think I would mind 1,000 Mozarts, but I don't think I could stand 1,000 Einsteins. Anyways, the only way to get to that vision is with giant space stations. The planetary surfaces are just way too small. And then his rival, another fellow who's doing some of the space stuff, Elon Musk, claims to be working towards making humanity multi-planetary and establishing cities on other planets like Mars. And so the question is whether we're going to ever make it to 1 trillion people, and whether we're ever going to make it to Mars or any of the other planets. I mean, not just sending a probe, we've done that, but the question is, will we be sending people there? And if we send people there, will it just be, like, yeah, we did touchdown, came back, that's great, but I mean, are we going to live there? Are we going to really terraform the planet or whatever? And that's a different story. I mean, if it's just a project to send people and say we did it, we have the technology to make it there and to stay there for a couple days, a couple hours, whatever, and then come back. Yeah, great, but I don't know if you want to spend $1 billion in such a project. But this is what these people are into. And as far as population is concerned, I don't know about that. Here you have, I was going to show you the global population. I guess I don't have it. Anyways, the issue is that population is grinding down. We're still increasing in the world. We're becoming more and more, but it's arithmetic. We're not expanding exponentially anymore. And so the question is, what's the end of all that? We're turning the corner, so to speak. We're approaching the asymptote. And if we don't have any growth in population, we have no demand. We have no demand or less demand, right? At some point, the global economy has to come to a halt in some way, one way or another. So you have to figure out what that implies for humanity. Okay, and fellow asks the question. He says, memetics, is it nonsense or is there a rational way of talking about it? And yeah, it's got to do with memes, and it's like an idea replicator. So if you're looking at this, it just means that just like, some things evolve over time, like humans, animals, etc., plants. The same thing applies to ideas. They go from mind to mind, and the thing spreads if it's, I guess, a good idea. I think that's the way they look at it. Yeah, you can talk rationally about it, but the question is whether what does that really mean? You had Marx. He talked about the materialistic dialectic, and before that, his teacher Hegel. He talked about philosophical dialectic, and it was the clash of ideas from where you get a synthesis, and so on down the line. And this is the same thing. It's just another version of what Hegel already put on the books. Yeah, you can talk rationally about it, but I mean, what does it mean? It just means that ideas propagate, I guess, if everybody buys into it, which doesn't mean that it's correct. You could have the flat earth notion, right? And it propagates, and yeah, okay, so does that mean we're all correct? That we have faithful reflection of Mother Nature's universe? So, the fact that ideas propagate doesn't mean that the ideas are rational. Okay, and I think that's more important. Okay, here we have a fellow, and he says, we haven't lost genetic diversity. Every human has a unique genome, except for twins, triplets, etc. As long as population is increasing, so is genetic diversity. Well, we take a different view here. We're saying that genetic diversity, humans have lost their genetic diversity, and essentially we're all clones of each other, more or less. That's where we are today. And here's evidence proof for those of you who like evidence and proof and want people to twist your arm, convince you. Here it is. This came out in 2012. You can look it up. There's a couple studies at least on this subject, and that's that chimpanzee populations living in relatively close proximity are substantially more different genetically than humans living on different continents. And what they showed really is that you've got these monkeys, these chimps in Africa, and they looked at a troop of like 100 of these animals, and they discovered that they have more genetic diversity within a troop than the entire human race, 8 billion people. And so the question is, we're not a very genetically diverse species. And what's happened to us? I mean, we're 8 billion people. We should have more, one would think, right? More genetic diversity because we're so many. It's the opposite. We're all clones of each other. Whoever you marry today is your sister or your brother from a genetic point of view. And so what can I tell you? This fellow does not does not share that same thought. He operates with a different set of assumptions. And yeah, you reach different conclusions. But all I can tell you what we do here, and we're saying that we've lost genetic diversity. And why? Because we've been inbreeding for 200,000, 300,000 years. We haven't married any other species. We have not enriched our genetic pool. And here you see what happens when you do that, when you inbreed. Okay, and a lot of people don't really understand this, so it's good to rub it in. These are the Amish. They were like maybe anywhere between 500 and 1,500 people 350 years ago. Today there's 350,000, I guess, mainly in the United States. And they looked at a group here of about 40,000, which came from about 400 founders, the founders effect. It said for religious reasons, the Amish marry only within their community. The population remains primarily derived from the original 400 founders. The Old Order Amish in Lancaster, that's county in Pennsylvania, I think, represent one extremely large family with about 40,000 members. In other words, they're all from essentially the same families. They've been inbreeding for 350 years. They are a very distinct group genetically and culturally, and the genetic variation within this community is so narrow. And there you see some of the studies of some of the genetic studies that they've done. There's a paper on that. And I just want to show that there's about 30 problems that they found with their genes, similarities and things that are not very healthy. So the point here is that, if you inbreed, if you marry your sister and then your kid also marries his sister and so on, and down the line, well, at some point you're going to run into some kind of problem. And that's essentially what has happened to humans over the course of the last 200, 300,000 years. We've been inbreeding, and that has to have a deleterious effect after, so many thousands of years. And that's the argument we have here. So no, we are not a very genetic diverse species. And the fact that we have more and more people being born every day does not increase genetic diversity. You would think there's mutations that accumulate, et cetera, but you have to factor in founder's effects, and you have to factor also population bottlenecks. Okay, so, and we've had quite a few of those throughout history. Whether we're going to have some of them now, I don't know. Not maybe due to diseases as it was in the past, maybe, yeah, due to wars, but I think that's going to be a drop of water in the ocean. We're already probably beyond the point of no return. We're already gone. We're already equal. Equality, not in our social and economic status, but we are all equal genetically. So if that helps anybody out there. Okay, some fellow says here, I'm 100% sure Milei's president of Argentina, okay? Ideas will make the overwhelming majority of Argentina's people much better off relatively quickly, because I talked about Milei the other time. Milei just wants very small government with a lot of liberty and opportunity. No, not no government. Charity naturally returns into churches, black markets will disappear, standards of living will begin to rise. Okay, I've got a problem in general with libertarians and what I call narco-caps, the anarcho-capitalists. Do I disagree with their ideas? Not really. That's not where the issue is. What Milei is introducing into Argentina might be good. You know, I don't know. We'll have to see that in the future. For sure, we can be sure one thing. In the near future, it's going to be very rotten for the Argentines, okay, for the people living there. It's going to be a big blow to a lot of poor people, especially, okay? And that's already a foregone conclusion. The government even says that, you know, it's going to get worse before it gets better, okay? Now, whether it gets better, that's in the long run. But as one economist once said, in the long run, we're all dead. So we don't know what happens in the long run. Those are wishful thinking on the part of a lot of these libertarians and narco-caps. But my argument is a little different, and that's that the whole planet, forget about Argentina, forget about Indonesia, Pakistan, you know, all these countries are in a serious condition. Their economics are terrible. In fact, the U.S. economy is quite terrible. The other day I was reading that the debt, the interest on the debt is surpassing what we're producing, the added GDP. And so we have to look at that. And a lot of that GDP is not real manufacturing or solid things, you know, tangible things, but they're services. So we're creating a lot of services that goes to GDP, but it's just a balloon that's growing that is not real growth. The real growth is in the material things. And, you know, manufacturing and a lot of stuff related to tangible things like houses, roads, etc. You know, that's cities growing, etc. You know, that's not growing at the same pace as the economy either. So the question is, you know, whether the policies that they will implement in Argentina will have any effect in the long run. Meaning, you know, will extinction come before any of those policies really have any effect? Okay, so, you know, again, we don't know what the future brings. I can only tell you that we're going extinct, and I can't tell you when, but it's just around the corner. We're not that far away. And so I don't know which will come first, whether the good results from libertarian politics or extinction. We also have the situation where we're having several wars today on the planet. The empires are clashing. You know, the empire of Russia, the empire of China, the empire of the United States. These empires are coming against each other. You know, they're trying to encroach on each other's economics and region of influence, etc. And who knows what that will bring, you know, how that will turn out. So that's another thing we have to pitch in. I mean, for all we know, this is the last year of our lives, right? 2024. Think about that. Something to think about. Dompa says, nothing can have a value. Nothing cannot, is when humans will become extinct. Okay, so yeah, it's becoming digital. We have some digital money, right? Already there are no logical people who place value on digital text or anything. Okay, great. Money, in Mo thinks that is, okay, and so he reaches this conclusion, and by money being no more, equaling humans becoming extinct. Yeah, I mean, if you take it in that direction, I guess that's the conclusion you reach. But I disagree with this fellow's assumptions. Okay. Okay. Follow continues, and he says the following. He says, "You said species is a concept. Absolutely. And extinction refers to a species. Right. To a species. Okay. What about the universe? Well, the universe cannot become extinct because the universe is not a species. It's not a living entity. And the word extinction here is not like when you say, oh, you used a fire extinguisher to turn, to blow away or extinguish the fire, right? It's not in that sense. And so when you use that sense, then you're obviously going to get some kind of contradiction. No, we're talking about extinguishing in the context of a species, which means that the last member of that species finally dies, okay? And there's no more of that species. That's what we call extinction. And so to take it and apply that same notion and extrapolate it to the universe, now we're talking about something else. What if it became extinct? Yeah, again, you can't say that the universe becomes extinct. I guess he's trying to say that the universe does not become extinct, does not exist anymore. And again, we can't say that about the universe because universe is matter and space. It's a concept, it's not a thing. Yeah, you can say that matter disappears, somehow becomes space, converts into space, morphs into space, fine. And then that's not the same thing as saying it became extinct. Okay, it just doesn't exist. And so you use exist for this and extinction for species. You should not confuse those two terms. But this fellow apparently does. He says extinction refers to anything. No, absolutely not. Extinction only in the ordinary speech refers to anything. When we say we extinguish a fire, that's not the notion that we're using here. Okay, we're using the notion of extinguishing in the context of species, of living entities, or it could be plants or animals, right? Any type of species, yeah. Existence is the opposite of extinction and vice versa. Absolutely not. And extinction can happen in any manner, and this is just a logical conclusion of money becoming no more as dinosaurs becoming no more. No, money becoming no more is not that money became extinct. But this is what this fellow, that's where he's getting confused. He's using the term of extinguishing a fire in the context of, dinosaurs and vice versa. Extinction of the dinosaurs in the context of extinction of money. Dinos and money both became extinct. No, absolutely not. Okay. And so all I can say is, yeah, you got to keep your language straight and you got to define your terms very clearly. And you can't use the word extinction in the notion of ordinary speech, which is extinction of anything, where it is equated to exist, and so or non-existence. And so they say, oh, he ceased to exist, he extinguished himself, or he became extinct. And we don't talk like that. In physics, it's either a species or becomes extinct, or we don't use the word extinct in the context of saying that. An atom became extinct, or I don't know, the fire became extinct. You have to separate those two notions. Okay, let's move on here to some of the questions people asked that leads us to the subject matter of today. It's got to do with several subjects, but they're all related to physics. Let's go with the first one. Fellow says, the way I understand the block universe. Remember we talked about the block universe, meaning this space-time that started at the Big Bang and expanded all the way to today, and they treat it all as a single block, despite that they cut it into pieces of time, time slices, and these slices are growing, but then they take that whole shebang and they say, look, it's a block universe. They treat it as a single thing, like it's got no time, or it's in the present. The whole thing is in the present, past, present, and future, all in the present. That's what the block universe is. So this fellow says, the way I understand the block universe is that it's not the last frame. The block universe is the entire film strip, and it always exists, both future and past. Yeah, but see, if it's a film strip, then clearly you're talking about each frame being a single slice of time. Okay, so that's the first issue. So no atoms are being created or destroyed. They just all exist at the same time. Well, that's not what it is. Here you see why. This is from the official, world there, of mathematical physics. And you can see there, I think it's the second one there. First particles, and then first nuclei, first light, and so on down the line. So you can see that they're being created as we go along. It's not like it all existed at the same time. There was an evolution, according to the official version of atoms. At some point there were subatomic particles, then they bunched into atoms, and eventually into bigger things, objects like stars and galaxies and so on. So this notion that he's got that it's all that atoms have always existed according to the official version is not true. There's been an evolution according to the official version of particles into atoms. That's one issue. The other one is that that space-time is divided into slices. Those slices are slices of time. And you must understand that, okay, that they're slices of time. Time requires motion. You can't do time without motion. And not only you can't see it as a single block because it's divided into time, but we're adding new slices. The present is moving, so to speak. You're having new slices of time as we move along. So you cannot talk about a single block universe. And again, there's a contradiction there that relativity never resolved. In fact, St. Augustine already had talked about, the block universe. He invented the block universe, or at least one of the guys who came up with it first and wrote about it. Okay, and that was in the 4th century, 5th century. Water doesn't get tangled with water, one fellow says. Light doesn't get tangled with light either, and ropes don't get tangled with each other either. Okay. And here's the single thread that we're referring to. And the single thread essentially has all the properties that we see in our macro world. It has the properties of, of solids, liquids, and gases. And that's the assumption that we make, okay? Turns into these atoms, and the atoms then, form everything else. And there's your rope. You've got two twined threads, and builds all the atoms in the universe. But see, all these atoms, they have the ability to turn into solids if the thread there that's uniting them is very cold. In other words, low frequency. If it has a little more frequency, it becomes liquid, and if it becomes colder, in other words, low frequency means solid, higher frequency means liquid, and even higher frequency means gas. That's all that the rope does to all these structures. But the point here is that as this fellow suggested, the thread, we say that it already has the properties that we see in our macro world of gases, liquids, and solids. Okay? The only 3 states of matter known to man. Now, some people talk about, plasma, something like that. It's the 4th state of matter. And I think they're confusing it. They think some state in Canada belongs to the United States, and they say that's the 4th state. I don't know. Plasma is not a state. Okay? Plasma is a dynamic concept, and therefore it's not a state, which is a static concept. Okay? We don't need to have gases move. We don't need to have water move. We don't need to have solids move. But we absolutely need to have something in motion to have plasma. And people like the electric universe, they never figured that out. Okay, so here we have, sorry, Bill, but your rope hypothesis is complete bunk. Oh, okay. It is physically impossible. Okay, he's got to define what physically is if we're going to understand him, but he just gave an opinion there. Okay, fine. The complexity required for such a mechanism to work would be unimaginable. I don't know why he has a low capacity for imagination. We've illustrated it. So, I have no idea why he cannot imagine it when we've drawn it, and he could just look at the picture, or watch the film strip. Okay, nature never does things the hard way. Well, there we agree, right? You will have no real mechanism because you are making assumptions based on what? Irrational ideas. Yeah, if we know what he means by irrational, it's easy to say irrational. He's just giving his opinion. He said anything that doesn't agree with him is irrational. That's all he's saying there. Unless he defines the word irrational, we don't know what he means by that word. Okay, so all he's giving us is his opinion. You're saying if quantum mechanics can suggest BS, so can you. So can I, yeah, okay. You still need to explain how your gazillions of threads could possibly coexist without being entangled. And that's this whole problem. That's this whole stumbling block. He cannot understand intangibility. That's the whole issue. And again, the problem there is that we have to have a definition for what an object is. And an object is not that which you can see or touch. My biggest contribution to science, by the way, an object is that which has shape. And an object has shape does not mean you can see or touch it. We can't see the air, and we can't touch, the chair that we can't see the air, and we can't touch the chair on the other side of the universe, right? And so we can't touch it. That means that the chair is not an object. The word chair does not refer to an object always. That's the question. And that's the first issue. Okay, but then he continues and he says the following. He says, your model doesn't explain much and requires some sort of intelligence to know how to pull or to twist, like some biological organism. I don't know where he got that. Obviously, he doesn't understand the theory, the proposal here. But he continues, he says, how can an atom know which atoms to contact and which threads to use? How does a flashlight know which atoms to illuminate on the wall? Well, we've illustrated this. Here's an illustration of that, of what he's asking there. And here you see it. All atoms are already connected before you turn anything on. Okay, so before you turn the flashlight on, the atoms are all connected by electromagnetic ropes. Every atom on the wall is connected to every atom, in this case, of the medium that's put in between, which in this case is a pin. Okay. But every atom of the pin is connected to every atom of the wall, and every atom of the flashlight is connected to every single atom that makes up the pin. So what you have is a relay mechanism. And what he cannot imagine about this, only God knows. Okay? It's very straightforward. All atoms are physically interconnected, so the atoms already know in advance. Why? Because they're already connected in advance before you turn on the light. And all you did when you turned on the light is stimulate those ropes to torque at a higher frequency. That's all you did. And you bring it into the realm of visible light. That's all that's happened there. And again, the wall, every atom of the wall is also connected to your eye. That's why you can see the essentially the reflection. What is reflection? Just you're relaying the signal from the flashlight first to the wall through the pin, and then from the wall directly to your eye. Those atoms are pumping at a higher speed, meaning they torque the rope at a higher speed, and now they bring it into the visible range. Okay, so it's straightforward. But this poor fellow, I guess, either hasn't taken the trouble to understand it, or doesn't understand it because he doesn't have the sufficient gray matter. And the funny thing about it, his moniker puts the word psi, like for science. What is a person like him doing in science? And here you can see he continues here. This fellow kind of answered him. He put another comment there, but essentially answers this previous fellow. Okay. And it says, if people can't see it or touch it, they assume there's nothing there. That's the whole problem, okay? I say this to them. You assume, I see nothing, therefore there is nothing to be seen. I know of nothing, therefore there's nothing to be known. My conclusion is that they, referring to these people who think in this way, they're fundamentally different type of humans. Okay. Yeah, this was a different type of human. Maybe he's not human. I don't know. Maybe he comes from a different planet for all we know. Okay, and this fellow continues. He says the following. He says, someone already proposed the only rational mechanism. Again, we don't know what he means by rational or irrational. For gravity and electromagnetism using a universal what? Continuous fluid medium. Continuous fluid medium. That's like a contradiction or self-contradiction, because if it's continuous, it's not fluid, and if it's fluid, it's not continuous. Okay, but he doesn't understand that. Okay, continuous means made of a single piece. That's what continuous means. Okay, and fluid means it's made out of particles or subunits. And so he's got a made out of a single piece thing that has many parts. That's what he's saying there. That's the kind of medium he's got in the back of his mind, if he's got one. Not made of any discrete constituents. Constituents, he put, okay. So there's a contradiction there. You can't have discrete units and be continuous. Either it's discrete or continuous. Those are two contradictory notions. And again, he's never figured that out. And fluid, any fluid has to be made of parts, no matter what. There's no such thing as a fluid made of a single piece, unless you make that assumption, okay? But if you're just going to talk about fluids like everyday fluids like water or oil or whatever, then it's made out of atoms, out of particles. And so you have to specify very well what you mean by fluid that is made out of a single piece. At least you have to make that assumption. No problem if you make that assumption, but make sure you don't talk about fluid in general, because when you talk about fluids, you're talking about molecules and something made out of many molecules, many atoms. And then in that case, it's made out of parts and it's not continuous. So again, he's got to resolve those contradictions that he's got there. But he says the following: says, Michelson-Morley experiment did not disprove the ether in any way. They did not know what it was, meaning the ether, right? They thought it was some sort of fixed fabric. Okay, so it's not a fixed fabric. What is it then? In the alternative, has he told us what it is? Did he put a link and show us what he proposes the ether is, so that we can all see it, with our eyes, and say, okay, I know what you're talking about, and I see what's going through your mind because you showed me a picture of your version of the ether, right? He didn't do that. He just says, oh, these people didn't know what the ether was. Okay, let's see what he says it is. Says they did not know what it was. They thought it was some sort of fixed fabric. To disprove the ether, you first need to have a pretty good idea of what the ether might be. Yeah, why don't you tell us? It'd be nice if he would have told us. He said, look, this is the ether, and pointed to a picture of the ether, right? And another fellow goes in there and also kind of doubles down on it, says, someone, what is it? Let's see, I got the right one. Oh, I got the same one. Anyways, I put the wrong one in there. But another fellow essentially came up with the same thing and proposed the ether. And so the question, what is this ether? And neither one of them put a link to a picture where we can see what they're talking about. They just talk about it. One guy said it's a fluid. The other one says it's a bunch of concepts. We don't know. We don't know what they're talking about. And again, I define an etherist as a person who does not know what the ether is, or who cannot define the word ether, or who cannot make a picture of the ether, cannot point to a picture of the ether. That's an etherist. Because the only thing an etherist never does, and never has done on this channel, we've gone through gazillions of etherists here, and not one of them has ever come up with a picture of what they're talking about. So if the ether is a medium means you're going to draw it, you're going to make a picture of it, take a snapshot, paint it. We need to see an image. And if you cannot come up with an image of the ether, don't talk about the ether. Or don't treat it as a physical object, as a medium. Now, if you're going to define the word and say, look, this is the ether, and you define it, then you can't use it as an object. You can't say the ether vibrates, because concepts don't vibrate. Either it's a concept or an object. There's no other category. Either it's an object and you draw it, you illustrate it, and you treat it as a medium, as a thing, or it's a concept, which is a relation, in which case you can't use it as a thing. You can't say it's going to vibrate, it's going to move, it's going to do anything. And they don't understand that. That's the first part. So that means they haven't gone through kindergarten physics before they open their mouths. Okay, so what is the ether? Well, I think I have it here. Give me a second. Yeah, here it is. Okay, so we're going to compare the ether against the rope so that they understand what we call the ether. You don't have to agree, but then your solution is to point to the ether. Just point to a link somewhere on the internet. You can upload it. You can put it to somebody else's. I don't care. But put a link to a picture if you're going to treat it as a medium Medium meaning it's an object, meaning it's got shape. We want to see an image of this famous ether. Otherwise, you define it, in which case it's a concept, and when you can't use it as an object. Okay, so here it is. This is the ether, a bunch of particles. They're discrete particles. They're not continuous. And are they fluid? Yeah, they're fluid because they're made out of particles. And compare that to what we propose, which is interconnected atoms. They're all connected. Okay, you can see the atoms there. They're all connected by something there. So you can see these two assumptions are totally different. The ether, bunch of particles that vibrate or whatever, and you have to tell us what the black stuff is that's giving shape to each one of those particles. So we need to know what the black stuff is. There's two things there on the left-hand side. You see some white little things that are moving around. Quantum would say they're popping in and out of existence, fine. But that's the ether, okay? And we're suggesting something else. We're making a different assumption. We're saying that what we have out there in the universe is a bunch of atoms and they're all interconnected. So these two things are different, okay? And so if you don't like the ether that I put there, you're saying, that's not my ether. You're wrong, Bill. Don't tell me I'm wrong. I want to see the ether, your ether. Don't tell me that you know what the ether is and that I'm wrong. Tell me what the ether is. And for that, if it's a thing, I want you to point to the image, okay? Give us a little picture, some link that shows the ether. And if you don't do it here, I'll do it for you. Okay, one more time here, I'll show you the ether. And this is not from mine, okay? This is if you Google, doing images, right, on Google, and this is what you get for the ether. You get all these little ethers out there, what people think the ether is, okay? And you can see that this is what Michelson and Morley worked with, okay? And the specific ones I want to show you are the ones that have all those arrows pointing in a given direction across the Earth. And what they're talking about is particles. They're saying there's this sea of particles, essentially a sandbox. Okay, you go to the kids' playground, you find a sandbox. That's what it is. And so for some reason they have these particles vibrate. I don't know why, but that's what the ether is, a bunch of particles. And what Michelson and Morley were trying to figure out is if there's a difference in light traveling against the ether at 90 degrees versus traveling, in the same direction as those particles. That's what it was all about. And they showed no difference, so they said there is no ether. And these people say, oh, the Michelson-Morley experiment was wrong. Okay, no problem. Then show me first your ether. Then we know what you're talking about. Until you show me your ether, we have no idea what you're talking about. Okay, so the onus is on you. The ball is in your court. Okay, so you've got my ether for you. Since you don't put the ether, I put it for you. If you don't like my ether, you put yours. That's how simple it is. Don't tell me I'm wrong. I know I'm wrong. I'm always wrong. I want to know what's right. Okay, so put your ether. Don't tell me I'm wrong. Okay, here we have what's his name, Mr. Brian Greene. We're going to start our gyroscope / gravity probe B lecture. So here we start with Mr. Brian Greene, who presented that in one of his series. Okay, and that's why I want to put this all here. Brian Greene, this is his brief bio. I got it from different sources. Is a string theorist and mathematician. Greene was a physics professor at Cornell from 1990 to 95 and has been professor at Columbia since 1996. So he's been around for a while, right? 28 years now. He is chairman of the World Science Festival, so he's quite popular, right? Also a popularizer of physics, so-called physics, mathematical physics, irrational physics, right? Greene has become known to a wider audience through his books for the general public, The Elegant Universe, Icarus, etc. The only one I'm going to mention there, The Fabric of the Cosmos, because I'm going to be looking at his, I think it was his fourth installment on that series, and that was, he talked about space. But in that same space that he analyzed, he talked about time. And why? Because he talked about the gravity probe B, which was used to put, to know where to put the satellites up there, for GPS. So it was an important experiment. that showed where to put the satellites, but it does not explain how all that works. So to this day, none of these people can tell you, how GPS works. They tell you, look, all we know is that when we measure, there's a difference in time when you put the atomic clocks in those satellites up there in the sky. They have no idea why. What causes, the clock to go slower or faster, the ones on Earth versus the ones up there. Okay, so what we're looking for is explanations, mechanisms, causes. We want to know why. And that's an answer that no mathematical physics on planet Earth, with all the GPS we have out there, can answer for you. Okay, so that's the issue. Okay, the issue is mechanism. Okay, that's what we talk about here. We talk about physics, not math. Okay, and when they tell me that time is dilated and time is bent and I don't know what, they're not talking about physics, because time does not belong to physics. Physics, we do not use time because time is a description, and in science we explain. We do not describe. Okay, so here we have, this is what he tried to show, that NASA gyroscopes prove Earth drags what? Time around itself when it spins. My God, it drags time around. And you say, Bill, is this true? Is this what they try to show? Well, here's a picture of what they're suggesting, right? Time is being dragged around. Okay, if this is what they think, I mean, what are they dragging? The seconds, the minutes, the seconds, right? So we need to know what they're talking about. And here's from respectable sources, authorized sources. Here you say it. This is NASA, frame dragging experiment, okay? And it says direct evidence that the Earth, drags space and time around itself as it rotates. Now, I didn't invent that. This is out of authoritative sources. The research is the most accurate direct measurement to date of the effect, bizarre effect of general relativity, which predicts a rotating mass will drag space around it. So every time you turn around, you're dragging space. Forget about air, but you're dragging space as well. Okay, I guess you got to spin fast enough to notice the difference. As the Earth rotates, it pulls space time. So it's going to pull time as well. Okay, I want to make sure they like to talk about space, and they leave the time usually out, because if they just talk about dragging time around, people would say, "Ooh, that doesn't sound right." But when they say space, people think it's a physical object. And so, they can get away with more by saying space. But here we're going to show that they're talking about space and time, and they call it space-time. And what they're really talking about is not dimensions, not coordinates, not vectors. They're talking about number lines. What they're dragging around is number lines. Okay, so here's the gravity probe on the right. It says, this comes from the Wikipedia. The gyroscopes were intended to, reveal how space and time are warped by the presence of the Earth and by how much the Earth rotation, drags space-time around with it. Now, I didn't invent this, okay? This is out of all these sources, right? And then at the bottom, there's another source there. It says, in general relativity, mass's rotation influences the motion of objects in its neighborhood. Put simply, the rotating mass drags along space-time in the vicinity. Okay, now, what is it that I didn't understand? Okay, yeah, they're saying you're dragging time around, and you're dragging space around, which is nothing, but they claim that space is this physical object, three-dimensional object, and so people get confused. They say, well, yeah, I can probably imagine it dragging a three-dimensional object around. But when you say just time, they say, what do you mean you drag time? And that's why they don't talk so much about time. They talk more about space. And just in case, here we have Stephen Hawking. He clarifies for us, just in case you missed it, that space and time, there are no differences between them in the religion of mathematics. Okay? And here it is. He says the following. He says, in relativity, there is no real distinction between the space and time, coordinates, meaning number lines. They're not talking about coordinates. They're not talking about length, width, and height, or about latitude, longitude, and altitude. They're talking about radius, width. They're talking about numbers, and what they're talking about is number lines, and they call them dimensions or coordinates or whatever word they put in there. Okay, so they're saying there's no difference between space and time coordinates, meaning number lines, right? Yeah, of course there's no difference, not in number line. There is a difference between a coordinate and a dimension, but the mathematicians never figured it out that coordinates and dimensions refer to different things. Dimensions refer to, length, width, and height. There's a directions in which, perpendicular directions in which an object faces or points. And coordinates, the arrows go in the opposite direction. They go from the walls of your house towards you. That's your location with respect to your house. If you take three perpendicular, arrows coming towards you. Okay, so that's different. But mathematicians treat coordinates and dimensions and time and everything all the same because they're all number lines. They're not dimensions. Okay, so where does good old Brian Greene start when he talks about this subject about dragging time around? Well, he starts by showing that there was a little bit of a difference between Newton and Einstein. Okay, so let me put this up here. And what I've done is I've karaoke'd it behind. So all these will have my voice in the background, but they're the exact words used by Brian Greene in his exposition, in his series. So here it goes. Listen carefully. There it goes.
Back in Newton's time, space was just a container. It didn't do anything at all. Then, through Einstein, space begins to affect how objects move.
Okay, so they're starting with Einstein, right? He's starting to treat space and time. Keep in mind, they're talking about space-time. They leave the word time out because that would create a little bit of a problem with a lot of people. And so they talk about space being able to move and shove things around. So now it's no longer this static thing. It's got this ability to push things around, okay? And here he rubs that in. Again, let me show you this. Here it goes. Listen carefully.
Where Newton thought space is passive, Einstein saw it as dynamic, interwoven with time, and it dictates how things move. So, after Einstein, space can no longer be thought of as a static stage. It's an actor, and it plays a leading role in the cosmic drama.
Okay, and here you can see this comes from Stephen Hawking's book, and he does say that space and time do actually move. So, there's no contradiction between what Brian Greene says and what Hawking says. It says, before 1915, space and time were thought of as fixed arena. But then he says space and time are now dynamic quantities. When a body moves or a force acts, it affects the curvature of space and time. And in turn, the structure of space-time affects the way in which bodies move and forces act. Okay, so you see this argument from mathematical physics. So they all agree, the mathematicians, the so-called mathematical physicists, they agree that they're saying space and time move and they have the ability to push things around. Okay, that means time pushes on you. They're treating time as a physical object. Let that be no ambiguity about that. In fact, if you're going to drag time around, which is what gravity probe B essentially proved, frame dragging as they call it, if you're going to drag time, it had better be a physical object. And so that's what they're saying here, okay? I want to make sure everybody understands that. They're saying that time is a physical object, like a rock, or like a tree, or like a dog, or something that you can drag, right? Okay, and here he continues, he says, space is not nothing, meaning time, right? Remember, it's space-time, right? He's saying it's not nothing, it's something. And here it is. This is all out of their own, this is the horse's mouth speaking there. I'm just speaking in the background because I'm just saying the same words that they're saying. And this is all textual. This is all verbatim. Here he goes. Listen carefully.
What if you took away all the planets, stars, and galaxies? And not just the big stuff, but tiny things. What if you took it all away? What would be left? Most of us would say nothing. And we'd be right. Strangely, we'd also be wrong. What's left is empty space, and, as it turns out, empty space is not nothing. It's something. Space is so real that it can bend, space can twist, and it can ripple. So real that empty space helps shape everything in the world around us and forms the very fabric of the cosmos.
Okay, so there you have it. Space and time are physical objects. And he reinforces that throughout his whole exposition, his whole lecture, his documentary. Okay? And just in case, he wants to show you an argument that he's got of why space and time, remember space time, but he's going to talk mainly about space, but don't let that confuse you. He's also talking about time. He's saying that this thing he called space, this thing he called space-time, is a physical object because otherwise, you have a skater and she's skating around. What is she moving around with respect to if you remove all objects in the universe, all atoms, everything? And here, this is the horse's mouth talking here, okay? And let me put them on. Here it goes. Listen carefully.
Let's imagine that you could take all the stuff in the universe so that the only thing left is a skater spinning with respect to completely empty space. If the skater still feels her arms pulled outwards, she'll know she's spinning. But if empty space is nothing, what is she spinning in relation to? When she spins, her arms play out because she is spinning with respect to something. And that something is space itself. Scientists came up with a bold new picture of space. The key was to make something out of nothing.
I absolutely love that last statement. Yeah, they had to make something out of nothing. So we have nothing out there, but they said, well, if she's spinning, what is she spinning with respect to? And that's why they turned space, time, right, into a medium. Because otherwise you say, well, what is she spinning with respect to? And so they had to turn nothing, which is space, what space is, or not, into something. That's what happened. Okay, and just in case he comes up with another bit of proof, evidence, and that is that all atoms are mostly empty space. Okay, so here goes. Listen carefully.
You can take the most abundant thing in the universe, even the tiniest of things, like atoms. Even they are almost entirely empty space. In fact, if you remove all the space inside all the atoms making up the Empire State Building, you'd be left with a little lump about the size of a grain of rice, weighing hundreds of millions of pounds. The rest is only empty space.
So where did they get that? Well, they say Rutherford ran some experiments, what was it, 1919, and he figured out that an atom is mostly empty space. And everybody just repeats that today without thinking about it. If an atom is mostly empty space, meaning there's a ball in the center and a little bead going around it, you have to explain why the bead doesn't fall, negative bead falls to the positive nucleus, or why the negative bead doesn't spontaneously fly away. They never explain that. They just say it's mostly empty space, meaning between the electron and the proton. And that's just a statement. It's an irrational statement because they can't justify why that bead stays faithful to the proton, despite being, one positive, the other one negative. It should fall directly to the nucleus, or why does it fly spontaneously away? And of course, they'll never answer that kind of question. But it turns out that if an atom is mostly empty space, what is space? Well, it turns out that space, according to them, is made out of particles. And again, this comes not from me, okay? This comes from good old Brian Greene in his show, and here he goes. Listen carefully.
According to the rules of quantum mechanics, even if you try to remove every last atom and particle, you'd find that empty space is still far from empty. In fact, it's teeming with activity. Particles are constantly popping in and out of existence. They erupt out of nothingness, quickly annihilate each other, and disappear. In quantum mechanics, empty space is not that empty. It's full of fluctuating fields, full of all sorts of jittery things going on. It's a place where particles are constantly fluctuating and annihilating each other, and being created again and annihilating. It's a place of chaos and bubbling.
So what is empty space made out of? It's made out of particles. So we have particles such as an atom, which is mainly empty space, and then empty space is not empty because it's made out of particles. Great. I mean, we've learned a lot with these people. Okay, so they ran this gravity probe B thingy, and they proved with it that space is a physical object, meaning space-time. Keep in mind, this always includes time. They just don't mention time because it's taboo. It's kind of more obvious if they just talked about time, so they talk about space, which is easier to push across to people. Okay, so this is what he says about it.
This experiment buys the most direct evidence ever found that space is something real, a physical entity, like a fabric. After all, if space were nothing, there would be nothing to twist.
So yeah, if you're going to twist space, like he said originally, that you could twist it, bend it, send waves through it, well, if you're going to twist it, it had better be a physical object. So I think there's no, I mean, he reinforced that in so many ways that you cannot say he did not say it. He did say time, space, space, time, physical object. It's a thing, okay? He never defined what a thing is, but he's saying it's a thing, meaning you can touch it, because he's saying space can push on you, meaning space-time can push at you, meaning time can push at you, because time and space both move, and they're malleable, and all these good things. Okay, so here they came up with this experiment to prove to people, to the general public, that space and time are physical objects, and you can actually drag space and drag time around the Earth, and it's called Gravity Probe B. That's how they're going to do it, and he gives you a little light explanation here there, but it really puts you up to date what the gyroscope, what your $1 billion, it was around 800 million, but this is, I think, conservative. I think they spent like $1 billion over like 30 years to develop this project. And this is what he's got to say about it. So this was the plan. They did it with these gyroscopes, perfectly round gyroscopes, and they're going to point, the axis at a star, and so they're going to try to figure out if, when Earth moves around, it drags these gyroscopes in such a way that it takes that axis off. Pointing to that star. And I think they did it with a laser. Okay, here goes. He's going to explain it in more detail. Here goes.
Normally, a gyroscope's axis points in a fixed direction. But if Earth is actually dragging space, then the gyroscope's axis would be dragged along with it, shifting its orientation in a way that could be measured. NASA attached 4 freely floating gyroscopes to a telescope aimed at a distant star. If space twists, then over time the gyroscopes would no longer point at the star, since they get caught up in the swirl of space.
Okay, so that was the plan. That was the design of the experiment. they had a little bit of problem. They had a little bit of a problem because you really want to control that. You want to make sure that there's no change for some other reason that has nothing to do with the Earth dragging time around. Okay, so that was the issue. But it turns out they encountered a problem, and he states it. At least they were honest about that. And I want you to consider this when you factor whether they were honest or not, or whether they, kind of fudged the data to match what they wanted, their preconceived ideas for this. And here it goes. Listen to this.
For over a year, Gravity Probe B orbited the Earth, while NASA monitored whether the Earth would actually twist space. The data began to trickle in, and there was a problem. The gyroscopes were experiencing a tiny, unexpected wobble. And to clean up the data would cost millions. Over the next 2 years, the problem with the data was solved, revealing that the axis of the gyroscope shifted by almost exactly the amount predicted by Einstein's equations.
So there was a problem, and the problem was a big problem because we're talking about wobbling, and kind of like, that was what they were testing. And so if it's wobbling for some other reasons, then your experiment is all shot out. It's no good. But they're saying they cleaned up the data. You know what I mean? They cleaned it up, and they got rid of all the bad data. And it turns out, just by sheer coincidence, the deviation from the axis matched Einstein's equation. Coincidentally, what a coincidence, that's something you should keep in mind. Okay. Personally, I don't know whether it did or not, whether they fudged the data or not. It seems like they did, but I think it's irrelevant anyways, because again, their conclusions are what's important. And you would think that after all that testing, after doing all these experiments and looking at Einstein's equation about space and time, you would think they'd have a great handle on both space and time. Okay, so this is how good old Brian Greene concludes his presentation, and you really should listen to this, because this is his conclusion. This shows you how much they learned from all this about what space and time are. Okay, and here it is. This is how he ends his presentation. Here goes.
For something that is a vital part of our everyday lives, space remains kind of like a familiar stranger. It's all around us, but we're still far from having unmasked its true identity. That may take 100 years, it may take 1,000 years, or it may happen tomorrow. But when we solve that mystery, we will take a giant step towards fully understanding the fabric of the cosmos.
Okay, so after all that, he has no idea what space or time are, what space-time is. It's like they don't care. They just say it's a physical object because it can push you. Okay, they measured it. They showed that through an experiment that space and time, or time by itself, space by itself, pushed the gyroscopes aside and changed the axis of orientation there. Okay, so they did all this fancy stuff, and after all that's said and done, he still cannot tell you what space is or what time is. And in fact, here you have today's notions. Okay. See if I can find this here. These are confirmed by dictionaries and encyclopedias. This is what space and time are. So if you're taking notes, get a pencil and pen and write this down, because we're going to have it on the test on Friday. Here it is. Yeah, this is what space and time are. Outer space, or simply space, is the what? Expanse. Whatever expanse is the expanse beyond celestial bodies and their atmosphere. So what we have is an expanse, whatever that an expanse is. Outer space is not completely empty. Okay, we don't care if it's empty or not. What is it? But they're saying so they think it's a container, which is what Newton said originally. So they're treating it as a container. It's just a movable or a malleable container, right? Maybe like a balloon. I don't know. Maybe. It is a near perfect vacuum, whatever that means, because what's a vacuum? Vacuum is made out of particles because vacuum is space. So I don't know what they're talking about. Unless they can draw this entity they call space, vacuum, nothingness, then we have no idea what they're talking about. Containing a low density of particles. Containing or made of? That's the question. I mean, is space a container, or is it made of particles, like this guy said originally? So they have all these contradictions. Space is a container, but it's a container of what? It's a container of atoms, etc., galaxies, whatever you got in there. But then space itself is made out of atoms, according to them. And so we have this circular argument. If it's made out of atoms, what's between, or about, not atoms, but particles, what's between the particles? Because when I have two particles, here I have two particles, right? Here, let's call these two particles. Well, hopefully there's space between them, because otherwise we wouldn't have discrete particles. There's got to be some medium that goes all around this ball for me to conceptualize this ball. And so if space is made out of particles, what's giving a background? What's giving what's contouring each one of these particles? So we still don't know what that stuff is that, gives shape to the space particles that come in from the void whenever the mathematician requires them. What is time? Well, let's find out. Time is the continued sequence of existence and events that occurs in an apparently irreversible succession from the past through the present and into the future. And the problem there is, if you look at the word past, present, and future, they're defined in terms of time. So we have a circular definition. Time is past, present, and future, and past, present, and future is time. Great, we've learned a lot. Defining time is in a manner applicable to all fields without circularity has consistently eluded the scholars. So that's a great way of ending your presentation. You start the presentation saying, we're going to prove to you and convince you that we know what we're talking about. And they end their presentation saying, oh, we're still researching. We have no idea what space or time are. But we know for a fact, through experiments, that the Earth drags time around itself, and so do you when you skate, turn around like a skater, twirl around, spin, you're dragging time around. Don't go into a carousel, a merry-go-round, because you're going to be dragging, time around yourself. And yeah, if you go to a carousel and spend some money there, you'll be spending a lot of time, believe me, you'll be dragging a lot of time around yourself. So that's the bottom line. They do these experiments and they come out with all these physical interpretations. When you point some of these things out to them, they end up saying, well, the fact is that all that's philosophy. We just do math. And then the question that you always should ask them is, why did you attempt to give a physical interpretation if it's not in your job description, if it's not in your line of work? Why did you give a physical interpretation? If you do equations and you call physics equations, no problem. But keep it within equation. Don't jump the fence into physics and say, I can tell you how the universe works, why it works the way it does. And you give they even illustrate it. And what they're illustrating is nonsense. They're illustrating what? That's what they're illustrating. How the Earth drags time around. That's what they illustrate. And so this is their conclusion. So you cannot say that these people have learned anything or know anything about time, that they can explain anything about how the universe works. And this is the bottom line, So, all you can say is that they still know nothing. With that, I'll see you next week, hopefully on Sunday. We'll see you then. Bye-bye.